All right. Can I make a confession? This is just between you and me. Please don't tell anyone. Like, I'd hate for this to get out, so I share this in confidence. I am a bit intimidated by neural networks. Yeah, I said it. They're all the rage now, these kids talking about their neural networks. And I feel like an old man being left behind. But you know what? I had a realization the other day. As I was microwaving a burrito, I thought to myself, I have a PhD. I have a doctorate of philosophy in quantitative psychology, which is like statistics. So clearly, I've demonstrated I'm capable of learning something before. So there ain't no need to be intimidated or nothing. So I decided it's time to find out what neural networks are and if they're useful for the type of work that I do. Because here's the thing, neural networks are everywhere. They are, or an expansion of neural networks, are what power ChatGPT. They can generate artwork like DALL-E. They perform facial recognition. And they power like freaking self-driving cars. They are the who's who of statistical models, man. So because they're everywhere, I decided to stop ignoring them and really learn what they're about. With you, kinda. Because I just learned about them, like yesterday. And so because I learned them yesterday, I'm just forewarning you, I am not an expert. This is not an expert tutorial. This is my curiosity-driven exploration from a statistician's point of view. And if there's any confusion, I'm the statistician of which I speak. So I'm going to focus on what they are, when to use them, and what we can learn from them. So let us begin with a brief history of neural networks and why they're called neural networks. So I guess you can trace the origin to the 1940s. There was a paper by McCulloch and Pitts, 1943. So what they were trying to do is they were trying to make a mathematical model of how the brain works. Or really, a mathematical model of a neuron. So this mathematical model computed inputs and then applied some threshold, and then using that threshold decided whether that neuron fired or not. So yeah, that was cool, but nobody really used it until the 1950s and 60s. With Rosenblatt's perceptron, which was a machine or a computer that was the first physical neural network. And so it was able to recognize patterns like basic shapes and stuff like that, but it was very, very limited in what it could solve. And essentially it could only solve linear equations. So if there were any curvilinear relationships, it was kind of stuck. And it wasn't multi-layered, which we'll talk about in a minute, because the math wasn't quite there yet. We didn't quite have the math for multi-layer neural networks. So it kind of fizzled out. Nobody really did anything with neural networks in the 60s and 70s. But then in the 80s, things started to happen. So in the 1980s, the mathematical answer to the multi-layer neural nets called backpropagation was invented. And so the mathematical foundations became there, but computers were slow and unstable, and the algorithms were pretty unstable, and you needed a lot of data. And over time, since the 1980s, computers have kind of gotten more powerful. And so now, modern hardware makes it possible to do these neural networks. So why did they call them neural networks? Well, the early goal was to mimic the brain, or mimic neurons firing in the brain. But today's models don't really resemble neurons very well. They're not binary like they used to be. So if anybody knows about action potentials and neurons and dendrites and all that, you know that neurons either fire or they don't. They're binary. Whereas neural networks contain more than just binary information. Also, they're not self-organizing like actual neurons are. So like neural networks don't create new pathways, and they don't evolve like actual neurons do. So basically, neural networks share very little similarities with what is biologically happening with neurons. But hey, it's a really cool name, so we just stick to it. And also, it conveys the basic idea that we have lots of very small, simple units that combine together to produce complex behavior. So now we get into the complicated part-ish. Like, what are neural networks? And you might have seen graphs like this. This is my graph that I made. So let's say you are interested in predicting muscle growth, which is that circle on the right there. And you want to predict muscle growth using 4 variables. Now, often neural networks have way more than 4 variables, but just for simplification, we're going to use 4. Protein intake, how many minutes they exercise a week, how many sets per week, and exercise ratings. And maybe you have a bunch of experts rating how good a particular exercise is at hypertrophy or muscle building. And so let's focus in on just N1 for just a minute. Now, if you are familiar with these sorts of diagrams, that might look a whole lot like regression. And it is. So we could call N1 our outcome, and we could write it like this: B0 plus B1 times protein plus B2 times minutes plus B3 times sets plus B4 times ratings. That looks very similar to a regression model. Yay! We're in familiar territory, people! Woo! But there is a slight difference with neural networks. B0 we're going to call bias, and instead of using B1, B2, B3, and B4, we're going to use W's. Why? I don't know. It's the same thing. They're still weights. But we're not ready to create the neuron, and instead we're going to predict something called Z, and then we're going to apply a second function, which actually is N. So N1 is equal to F of Z. Or in other words, we're going to take a regression model and then apply some sort of a function to it. Now, why are we doing that? That F of Z is going to introduce nonlinearity. If you don't introduce mathematical nonlinearity in the model, what your neural network ends up becoming is just a bunch of regression models stacked together, which means it's only going to be able to produce linear fits. And if you have any sort of complex relationship, it's not going to work. Some common activation functions are the sigmoid function, which looks like this, or the hyperbolic tangent function, which looks like this, or the rectified linear unit, or leaky rectified linear unit, or softmax. Anyway, there's lots of formulas out there we could apply to create nonlinearity. So that's the model for N1, but we also have a different model for N2, where it's going to have a different bias and it's going to have different weights. And same for N3 and N4. And so all these neurons are going to have their own individual weights that are all completely random. And their biases, or their intercepts, are also totally random. I don't know why they call it bias, but it behaves just like an intercept would in regression. So now we call that one layer. But sometimes we might want to have multiple layers. So like on the left here, we have lowercase n, and on the right, we have capital N. And by the way, this is my convention. I don't know what the actual convention is for neural networks. So you might be asking, hey man, why in the world would I have multiple layers? Good question. So more layers means there are more hierarchical representations. And that was a lot of words. So what do I mean? So what that means is that the early layers might extract basic features. And then the later layers might combine them into abstract patterns. So as an example, if you're doing image recognition, the first layer might identify shapes. And then the second layer might identify colors. And then a later layer might be able to aggregate all that information and then come up with a representation of a cat or a dog or a face. So each layer is coming up with a more refined representation of what's going on. And then finally you got the outcome, which in our case is growth. And that is where we basically have a simple regression model with a function applied to it. And by the way, that nonlinear function is called the activation function. So the final layer is used to predict the outcome. And it looks very similar to the individual neurons. We still have a bias, we still have weights, and we still have an activation function. All right, so that's the basic representation of what a neural network is. Now, how do neural networks learn? I could spend an entire series of videos communicating this, but I'm just going to go over the basics. So remember, initially, the weights are chosen totally at random. So neuron 1 might look like this, neuron 2 might look like this, neuron 3 might look like this, and 4 like this. And likewise for the next set of weights, and then the next set of weights. And then at the end of the model, we have actual growth measures. So the actual muscle growth in this example. And we also have the predicted growth from the model. So actual growth we might call Y, predicted growth we might call Y hat. And you might have seen this formula before, which is called the sum of squared errors. And basically it is a function that tells you how far off you were in predicting the outcome. Or another way to think about it is a measure of misfit in your model. Then what we do is we use an optimization algorithm. And this optimization algorithm is going to adjust the weights through something called backpropagation. And this is the really complicated part that I'm not going to go into details. But it uses a steepest descent algorithm, which I've talked about before. And I will link that paper in the description. So through this backpropagation process, each neuron is finding its own local minima. And so one way to think about it is each neuron is like a mountain climber. And by adjusting the weights at the beginning, it's like they're starting at a different side of the mountain. And as it is searching for a fit for the model, it's like it's traversing that mountain using the steepest path that it can find. Because that's the quickest way there. Which, that's kind of where the metaphor breaks down. Because not many people would choose the steepest way up the top of a mountain. Usually they choose the least steep, but you get the idea. And so each of them climbs the mountain using the steepest path until the path basically levels out. So they're going to end up on different parts of the mountain. And each of those neurons is going to learn something different depending on which path they take. So I know that part is a little vague, and that's okay because in order to explain it in detail, I'd have to get super mathematical, and I don't want to do that. But hopefully you get the basic idea. It's essentially using an optimization algorithm. So the question that I wondered is, when do neural networks actually make sense? Like, what use cases do we have? Well, there's the obvious ones that we've all heard about, like ChatGPT, which is for text generation. And so in this case, the input is the user's question, and the output is the next word that the algorithm puts out. So it's trying to predict the next word in the sentence. And after it predicts the first word, it's going to use that first word as an input and predict the second word. Again, with the user's prompt providing some feedback as an input. Likewise, we can use it for image generation, like using DALL-E, where the input is the user prompt and the output is a pixel at a particular location. And just like with ChatGPT, it's going to use its previous pixel decision as an input for the next pixel decision. And so I know about those, but I don't use those in what I do. I do science, garsh nabbit, dag nabbit. And so I'm more interested in data analysis. And so I started to ask, can you use neural networks for data analysis? And you can. But they tend to be used when you are interested in prediction, not in explanation, or not even interpretation. Usually you don't try to interpret these things. And I'm going to talk about that a little more later. So they tend to shine when you have lots and lots of data. And in my mind, I'm always comparing these to regression models and random forest models. And so relative to these models, when does it perform better? They perform better when you have lots and lots of data, apparently. So random forest can get pretty bogged down with lots and lots of data, but neural networks tend to do better, apparently. But more importantly, when you have really complex structure that is hard to mathematically model with decision trees, neural networks tend to do a pretty good job. And it's also really good with unstructured data. Like, as a statistician, I really like tabular data, meaning you have each row representing an individual, each column representing a variable. But if you have something unstructured, like images or audio or text, neural networks do really well. And they also shine when you really don't care about interpretation. You just want to predict something. And not surprisingly, they struggle under certain situations. Again, I keep saying this, they struggle when you want to interpret what's going on, which is often what we're trying to do in science. We want to interpret what the data are telling us. That's really hard to do with neural networks, and it's not designed to do that. They also struggle when you have a really small data set, and they struggle when, or at least they don't shine when your predictors already make sense, when you already have a good grasp of what your predictors are. So like the example that I used before, where you have protein intake and how many sets per week, etc. Like if you already understand the input variables, they may not do so well. So now let me give my statistician's take on my problem with neural networks. Speaking as a novice to neural networks, one of the first problems is they require a lot of tuning. And tuning means to adjust the parameters of the model. So you have lots of choices to make, like how many neurons should I have? How many layers should I have? What should my activation function be? All those things can yield very different results, which means it requires some expertise to tune the model in order to produce something that works. Another problem is they have a high risk of overfitting, which I suspect is why they don't do well on small data sets. Smaller the data set, more likely you are to overfit the data. And my biggest problem really has to do with the fact that they are very atheoretical. They're not designed to tell you why certain predictor variables influence certain outcome variables. And they're not designed to even tell you which variables are related. So for that reason, they're not really good at teasing out causation, which I would argue, and this is kind of a controversial point, less so now than it was 20 years ago, which that requires an extensive footnote, which I may or may not write in the description. But arguably, the purpose of science is to figure out cause and effect. And so if you're using neural networks, they weren't designed to tease out cause and effect. They were just designed to generate predictions. And so one might argue, and I don't know if I'm arguing this, but one might argue that they're not designed for causal inferences. Again, I'm not arguing that because I haven't used it yet. And they may be hacked to give you that information. I don't know. But at least at their core, they're not designed that way. And so in the end, it's really hard to tell what is useful with neural networks, what variables are useful. But they can also discover nonlinear relationships you wouldn't need to specify manually like you would in a regression. And also they force you to think in terms of representations instead of variables. Representations instead of variables. I'm going to say that again. Representations instead of variables. What do I mean? That's kind of an important point. And as a statistician who thinks in terms of variables, I had a hard time conceptualizing this. So traditional models focus on variables. So each input or each variable, each predictor variable, is treated as its own distinctive, unique, and interpretable feature that can be used to predict an outcome. Like how much does protein intake affect muscle growth? Neural networks don't focus on variables, they focus on representations. Each layer in a network is a new abstraction. And these abstractions aren't necessarily interpretable. So what they are is they are internal representations the model has created in order to solve the task. Whether it be text generation or image generation or model prediction. And every example that I've used in this video about representations have been things that I could understand. Like, okay, this first layer of neurons is detecting shapes, and this second one is detecting color, and this third one is classifying as cat, dog, human, monkey, whatever. But those are words that I put on it. Those representations that I'm creating might not be so easily communicated in the actual neural network. So instead of asking which variables are important, which is what statistical models tend to do, they are asking what internal structure or internal representation is going to help make the network better at predicting the outcome. So let's think of an analogy. Image representations. So let's say you're trying to do image recognition. So neural networks aren't just tuning weights. They are learning useful ways to take the input and re-express it to capture patterns that we don't see directly. So they are crazy powerful. And we all know they're powerful. Look at the amazing things that neural networks are doing. But that also makes them very, very hard to interpret. And I've mentioned this in the past with random forest models. They are black box algorithms, which means that something is going on in the background that we could actually dissect and look at the math, but that doesn't mean that we understand what's going on. Like random forests are creating all these decision trees and aggregating these decision trees. And we don't know why it's doing it, but it is. And it makes them really hard to interpret. Well, if random forests are black box algorithms, then neural networks are like black hole algorithms. Or maybe random forests are like dark gray algorithms, and neural networks are definitely black box algorithms. So that's the basic idea behind neural networks. Now, where do I go from here? I'm really scared to promise a video where I actually do a neural network, because I actually haven't ever tried it before. So I'm not going to promise it, but that's what I'm going to try to do, because I now have a conceptual understanding of how these work. And I would like to use it on real data and find out if I can see something useful come out of that. I hope. So that's the plan for the future. We'll see if it actually happens. Now, if you are interested in this sort of machine learning stuff, I do have a random forest course, which is also a data visualization course. They kind of work hand in hand, at least the way that I think about them. I don't have a live class yet. Oh, wait, no, I'm going to do it right now. I'm committing myself that in October, I'm going to have an artificial intelligence class that covers primarily random forests and data visualization. So if you want to join that class, see the link in the description. In those live classes, you get to interact with me through Zoom. It's pretty amazing, pretty awesome. We get to hang out. But you could also take my self-guided classes, and I will leave the links to those in the description as well. Anyway, I hope you have enjoyed this quick and dirty intro to neural networks. And yeah, leave your comments and questions in the discussion, especially if I said something wrong. Because like I said, I'm new to this. So if you are like a expert in neural networks, let us know what I messed up. All right, peace out.
Oh dear. We've got ourselves in a bit of a predicament, don't we?
Hey, you know what? If it's useful, who cares if it takes over the world? Who cares if it uses our bodies as batteries? If it could make a reservation for us at a restaurant. That's all I've got to say.
Excuse me, but, clearly you should have used a stepwise regression model instead of a neural network.
Stepwise regression? That's like taking a 115-year-old Olympian sprinter who competed decades ago and putting him against Usain Bolt. Questions are okay. What I get angry about is when reviewers don't ask questions, they make accusatory statements or implied accusations like, wait, you used this model. Why didn't you use this model? Clearly, everybody knows this is the superior model. Like, I love it. I love it when non-statisticians try to tell me the proper way to do statistics. It happens all the bloody time. It's like your drunk uncle on Facebook telling everybody that he is an expert in health because he watches RFK online. And Dr. Berg, that chiropractor gone keto nutrition advice expert. Yeah, it's all made up crap, that's what it is. That's the biggest problem we have now is everybody claims to be an expert and nobody knows what they're talking about except the people who know what they're really talking about. But the people who really know what they're talking about may not have enough charisma to compete with the pseudoscientists and supplement sellers and stuff. What do I look like? An expert in stats or something? Turns out I am.